All right, so this video goes with the second part of section 2.1, so day 2 of the notes 2.1. And generally, it's still talking about location in a distribution, but more specifically, this will be discussing how we can transform data. So if we do, if I'm going to curve a test scores, that kind of thing. And so how does this transformation affect things like measures of center, measures of spread, measures of location within a distribution?
All right, so this one's it's pretty straightforward, but let's say I asked everyone in class, assuming we were actually in a classroom, what is the width of our classroom in meters? And then these are the guesses. So this is a dot plot of all of the guesses of everybody. So some people guessed as low as what, 8 meters, and some people guessed as high as 40 meters, right? If we wanted to describe this distribution, remember we use SOCS, we use the shape, the outlier. We talk about the outliers. We talk about the spread, and we talk about the center in no particular order. So this is clearly skewed to the right. I would say the center. Now, it would be wrong to say the center is 15, right here in the middle. It looks to be about 15, but it wouldn't be right to say the center is 15. We have to say something like the mean or the median is 15. In this case, it would be the median is 15. Also, I can't say the spread is a certain value because we measure the spread using things like range or standard deviation. I think in this case I'll just use the range. And so we go from what looks like 8 all the way up to 40. So it looks like we have something like a spread of 32. Now remember, we don't say the range. The range is 32. We don't say things like the range is from 8 to 40. Range is a single number. It's the max minus the min. So it would be wrong to say the spread is 32. That would be wrong. You would want to say the range is 32. It would also be wrong to say the range is from 8 to 40. Range is the maximum value minus the minimum value. So it's recorded as a single value. There does appear to be outliers, in the right end or the high end, there does appear to be outliers. We're just asking to describe the distribution, so we may not have to necessarily find which ones are outliers, which ones are not. You could if you wanted. So let's see, we did center, we did shape, we did outliers, and we did spread. So we did the 4 things that we are required to do. And now let's look at what happens when we transform the data. So here again is the dot plot of all of the guesses in meters. And so the true width of the classroom, let's say the true width is 13 meters. So instead of recording everyone's guess, I might want to let them know how off they were from the true value. And so here we have the error. So in other words, 13, so again, 13 would be right here. So 3 people guessed 13. Notice those 3 people are right here on the 0 mark, right? So we transformed this data. We shifted it essentially 13 units to the left. We are using the same scale in both cases. Notice some values of the guesses, some people's guesses are negative, their error is negative because they guessed below the actual value. So anyone who guessed in the range of 8 to 12 would have negative error values, and you can see they showed up in the negative range down here. Okay, let's look at the actual data summaries for the 2 distributions, one the guess and one for the error. What values are the same and which ones are different, and by how are they different? So if we look the spread, if we just look at the 2 dot plots, you can see the spread really hasn't changed. So the range, the interquartile range, and the standard deviations are all the same, right? All of those 3 are the same. So the measures of spread that we're using have not changed by shifting the whole distribution down 13 points. But notice the measures of location. So like the minimum, the maximum, Q1, Q3, the median, and the mean, all of those measures of center and position did change, and they indeed changed by exactly 13. So if we kind of tie it all up, I think your slides on your handout were in reverse here, these two slides. So what happens when we add a number or subtract a number, A, from each observation? Well, it adds or subtracts A from the measures of location and center. We saw that. The mean, the median, the quartiles, Q1, Q3, the percentages would all change by that same value. However, the spreads do not change. All right, so now let's say, if I said, oh, your air was 2 meters. Well, some people don't really have a good sense for what 2 meters are. So let's take our data and convert it to feet. And we know that there are about 3.28 feet in 1 meter. So if I convert by taking each air value and multiplying each one by 3.28, I would get this. Now notice I'm using the same scale, right, on the bottom here. If you guessed 13, remember you would get an air of 0 meters. You would also get an air of 0 feet, right? So I'm trying to draw an arrow. That's not working. But you notice that those values did not change. But all the other values got a little bit more stretched out. Notice the spread of these dot plots are very different. And so the range, for example, if we want to look at the range, what happened to the range? Before it was 32, and now it's 100 and almost 105, right? So obviously that changed. And you notice all of these values changed. How did they change? Probably you can pretty quickly see that they all changed by a factor of 3.28. Sure enough, how many feet are in a meter? So each thing got multiplied. Each data value got multiplied by 3.28. Each of our number summary values got also increased by 3.28. All right, so let's tie it all up. So what's happening here? What happens when I multiply or possibly divide by each observation by a given number, and in this case we're just going to call that number B. So in our case we multiplied by 3.28, that's our B. It multiplies or divides the centers. So if I was dividing by, let's say I started with meters and feet and I wanted to convert to meters, then I would divide by 3.28. The reverse would happen, right? So instead of being more spread out, it would be less spread out. All right, so in this case you're multiplying or dividing, depending on what you did, each of the measures of the center, but also you'll be doing the same thing with all of the measures of spread. So the spreads all get multiplied. Now one little caveat here is that I suppose if you're going to multiply, you might be multiplying by a negative number. Can't think of an example off the top of my head, but if you're multiplying by a negative number, measures of spread cannot be negative, right? So the spread was 32. Notice I'm not just going to take that and multiply by B, which might be negative. So in this case, you have to do the absolute value of B because measures of spread are always positive. Standard deviation, range, interquartile range. Always the maximum minus the minimum for range, so it cannot be negative. Even if you multiply through by a negative number, the measures of spread would get multiplied not by B, but by the absolute value of B. All right, and then of course the shape still didn't change. If we looked, both of those distributions were still skewed to the right. So the shape didn't change, but they got more spread out, but the shape is still the same.
Okay, so with today's notes, we are besides the PowerPoint presentation handout notes, I also have a worksheet where we're going to practice a little bit more of the things that we've been talking about here, transforming the data. So let's look at number 1. Again, this is on your worksheet. taxi cab. So in 2010, taxi cabs in New York City charged an initial fee of $2.50. So that means if you just sit down in the cab, they're going to charge you $2.50. And they also then will charge you $2 per mile that you go in the cab. In equation form, this is the fare you pay is going to be $2.50 plus 2 times the number of miles. I imagine any part thereof, but you know, we'll keep it simple here. So at the end of the month, a businessman collects all of his taxi cab receipts and calculates some numerical summaries. So he calculates his mean fare, how much he paid on average, and it was $15.45 with the standard deviation of $10.20. All right, so what are the mean and the standard deviation of the lengths of his cab rides in miles? All right, so what we're going to do is we're going to think about working backwards, right? We have miles. We want to take our formula for miles, for fares, and we want to solve it for miles. So if we look at the fare equals $2.50 times 2 miles, 2 times miles, we want to solve that for miles. So we would what? We would subtract 250 from both sides and then divide by 2. So miles is equal to the fare you paid minus 250 divided by 2. So this is just taking the data and we're transforming it. So we're taking the fare data that we have, the receipts all have the amount he paid. They may not have the miles on it. So if he wants to figure out what his average miles were, he could work backwards. And that's what this problem is doing. It's taking the fare data and turning it into miles data, okay? And so we're doing transformation, a linear transformation. So to get the mean number of miles, you know, when you add or subtract and when you multiply and divide, both of those things affect the miles, right? The mean of the miles are the mean gets affected by both adding and adding and subtracting, but also multiplying and dividing. So we have to look at both of these things. So the mean number of miles, we would take and subtract $2.50 from the mean fare. So remember that mean fare was $15.45. We subtract $2.50 from that, and we will get $12.95. And then we take that and do one more thing, we divide by 2. So that gives us the mean number of miles is 6.475. That is the mean number of miles. Now let's think about the standard deviation, right? So the standard deviation for the fare was $10.20. What kinds of things affect the spread? Remember, standard deviation is a spread. And so remember that adding and subtracting don't affect it. So we don't have to worry about the 250. We just have to worry about the dividing by 2. So we simply are going to take the standard deviation of the fares and divide by 2 to get the standard deviation of the mileage. All right. So to find the standard deviation for the miles, we divide the standard deviation of the fares by 2, and we get 5.2 miles. All right. Again, we don't subtract the 250 because subtracting a value from a data set does not affect the spread. And remember that standard deviation is a measure of spread. All right, number 2. Here is a graph and table of summary statistics for the sample of 30 test scores. The maximum possible score on the test was 50. Suppose the teacher is nice and is going to add 5 points to each test score. How would this change the shape, the center, and the spread of this distribution? So they've given us a number summary of the raw scores, and now the teacher is going to add 5 to everybody's score. How will that? Let's start with the measures of location and center. So remember, locations, measures of location are things like the min, the quartiles, the max, those kinds of things. So notice that those measures, the measures of center, median and mean, and the measures of the location, quartiles, the min, the max, they all increased by 5 because we simply added 5 points to everyone's score. So you can think about that dot plot. Everything shifts over to the right 5 points. So all these locations would also shift. Now let's think about the spread. How will the spread change? How will the standard deviation, the interquartile range, and the range change? So you can see here they don't change because that whole dot plot is just shifting over. It's not more spread out. So the measures of spread do not change. Also, the shape is still going to be skewed to the left. It's not changing at all. All right, last question, dealing with Babe Ruth and the home run record in Major League Baseball. So, and the single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961. Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. In an absolute sense, Barry Bonds has the best performance for these 3 players because he hit more home runs in a single season, so clearly he has the record. However, in a relative sense, this may not be true. Baseball historians suggest that hitting home run has been easier in some eras than others. This is due to many factors, including the quality of the batters, quality of the pitchers, hardness of the baseball, dimensions of the parks, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to those other hitters during that same year. So we look at Babe Ruth, for example. He hit 60 home runs. What was the mean number of home runs in 1927 across the whole league? Mean number of runs per season per player was 7.2, with a standard deviation of 9.7. Okay, so to make a fair comparison, we want to see how these performances rate against those of other hitters during the same year. So that sounds a lot like we want to see where they were in the distribution, or maybe we could look at their z-scores. So we're going to compute the standardized score, that's the z-score for each performance, using the information in the table above. So the table gives you the year, the person who hit the most that year, the mean number of hits per player for the season, and the standard deviation. So let's do Babe Ruth. Let's do that calculation. So you can see the calculation for Babe Ruth is 60 minus the mean, which is 7.2, and divide by the standard deviation of 9.7. So that gives 5.44. So almost 5.5 standard deviations above the mean. That's way out there. I mean, that is huge. All right, so let's look at Roger. So his was 61 minus 18.8, and divide that by the standard deviation, which is 13.4, and he's only 3.16 standard deviation. So still pretty large. 3 standard deviations above the mean is pretty good, but here it doesn't even compare to Babe Ruth. All right, so then McGwire, his was 3.87, and finally Barry Bonds, who is the all-time highest at this point. So he's almost 4 standard deviations. So if you look and you compare them to Babe Ruth, as far as comparing them to how other people were doing in that same year, Babe Ruth is clearly the winner. All right, so the table shows the z-scores for each athlete. Although all of the 4 performances were outstanding, Babe Ruth can still claim that he is the highest based on a relative number of home runs for the rest of the players in the league. All right, so this is the homework for the second part of section 2.1. In some parts I might be calling this 2.1 day 2. But the second homework assignment and the only other homework assignment for this section 2.1 is number 18, 20, 23, 26, 29, and 30. That is due next class.